Yes. Yeah, so in continuation from where we ended, we're looking at the development of the atom. We ended at Niels Bohr. We said Niels Bohr was the leading contributor to the definition of the discovery of quantum mechanics. But the one that really did the work was Erwin Schrödinger, yeah, with a cat and all those principles. So for those that want to really understand how quantum mechanics works, there's a video, there's a documentary that I was playing. Now, unfortunately, you guys, we are saying you can't get what's happening. Like you can't get sound, shan. So I sent it in the group. If you feel you want to watch it, go ahead. Yeah, it's more informative. And there are a lot of illustrations, so it will be okay. So now, the quantification of energy was done by a famous scientist by the name of Niels Bohr. So he discovered, not really discovering, but because each and every, the atom was discovered by John Dalton. Now, everyone was coming up with ideas that build up the atom. We have J.J. Thomson talking about the discovery of the electron. We have Rutherford explaining the principle of alpha deflection and the noyau. We have Albert Einstein with the discovery of the photon. We have Niels Bohr with the definition of the hydrogen atom, because Niels Bohr's principle is basically based on the hydrogen atom. Then we have the last one, Erwin Schrödinger, explaining the variation of electrons in an atom. So now it's just a build-up for Bohr. Are there any questions or continue? Okay, so continue. So the first part of this school, we're going to look at the interaction of matter and rayonnement and rays. The second part will be the spectra de l'atome de hydrogène, diagram énergétique de l'atome, and the last part will be Bohr's model. But all in all, what I'll just do is I'll explain almost everything at a go, then we'll just reviewing some of the things. So basically, Niels Bohr's principle is based on 3 or bien 4 postulates. The first postulate states that an atom has got what you call energy levels, and these energy levels are stationary. These energy levels are stationary. That is the first postulate. The second postulate explains energy variation. So energy variation is in 2 forms. So you can actually call the second postulate to be divided into 2, or you can individually divide them just like that and say the first one, the second one, the third one, the fourth one, or you just go with the first one, the second one, which is divided into 2, then the last one. So they are divided, we have 3 postulates. You have 3 postulates. The first one defines the energy that are stationary for an atom. Take for instance, sodium. Sodium has an electron configuration of 2,8,1. That means the number of protons equals to 11. Then his definition was, because this atom of sodium has got an electron configuration of 2,8,1, it means that these electrons are found in stationary orbitals, and these stationary orbitals do not move. They are stagnant. They are stationary. They do not move. His second postulate was explaining the principle of energy absorption and energy emission, which is this part here. So we are saying that in the principle, this part, the first part here and the second part, there's a first part which explains the principle of energy d'absorption. So like I said in the later explanation about Albert Einstein's principle of the photoelectric effect, we were saying, take for instance, you have a source, and that source is radioactive. Now you are subjecting a particular metal to you're subjecting the radiation to a particular metal, and we are saying that a particular metal, take for instance, is copper, gold, any other metal, yeah? has specific energy that it has. It has a specific energy. So if the energy of the radiation is greater than the energy of that found in the metal, what are we going to have? We are going to have what is ejection of a photon. We're going to have ejection of a photon. Then if the energy of the metal is greater than the energy of the ray can also mean ray, the ray or the radiation, it means we cannot have any photon emission. So in other words, Bohr's principle was based on Albert Einstein's principle of the photoelectric effect, which states that, now this is what I explained, I don't know if it was in organic chemistry, saying in chimie atomistique, absorption is the movement of an electron from a lower energy to a higher energy. That is absorption. Emission is the opposite. It is the movement of an electron from a higher energy to a lower energy. In the English terms, emission is supposed to be the movement of an electron from a lower energy to a higher energy. This was supposed to be emission in the normal grammar. In the normal grammar that we speak, this was supposed to be the correct definition of emission. Then absorption was supposed to be this one here, where you have the movement of an electron from a higher energy level to a lower energy level. So basically, Albert Einstein's principle of the photoelectronic effect is this whole thing you are seeing here. So if the energy of a particle, is, for example, we are saying if the energy of the metal is greater than the energy of the radiation, it means there is no photon that's going to be produced. Therefore, it also implies that there is only going to be a transition or a movement of the electron from energy state number 1 to energy state number 2. What I'm trying to say is the electron found in energy state number 1 will be excited and will be moved to energy state number 2. I'll repeat. What I'm trying to say here, this whole thing explains Albert Einstein's photoelectric effect. So we are saying the photoelectric effect simply states that for a given metal or for a given type of radiation, they both have different energies. So if the energy of the radiation, take for instance, we're using beta or bien gamma, alpha or beta. If the energy of the beta or bien the alpha is higher than the energy of a particular metal, so we take this as a metal because metals like gold have electrons also. It's not like when they are metals there are no electrons. There's also amongst the bonding that we have covalent bonding, ionic bonding, we have metallic bonding. There is a fourth type of bonding. I've forgotten what it's called, but there's a fourth type of bonding. Yeah. So metallic bonding, we know that there's a sea of electrons and the delocalization of these electrons. So we are saying what happens is if the energy of the radiation is less than the energy of the metal, what this energy only does is it moves an electron, or bien it excites an electron. It moves it from one state to the other state. So you find me at some point in future will be saying, no, the electron was excited. So when it's excited, it moves from a higher energy level to a lower energy level, or bien from a lower energy level to a higher energy level, depending on which principle we are looking at. It can either be the absorption, it can either be the radiation. Now, we are saying energy de absorption is the movement, or bien the energy transition from a lower energy to a higher energy. So energy de absorption augmente énergie de l'électron augmente par l'absorption d'un photon. So instead of a photon being ejected, the photon is absorbed, and the absorption of the photon leads to the transition of this electron from position E to another energy level. Now, par contre, when you talk about emission is energy loss. So even when you're calculating height, when energy is absorbed, energy is supposed to be positive. When energy is emitted, it means the energy is supposed to be negative. Now, in the same sense now, you have an atom with a metal having a lower energy state as compared to the royon. So when this metal is subjected to an energy, for example, the energy is coming from this. If this metal is subjected to an energy, this metal is going to produce what we are calling a photon. L'énergie de l'électron diminue par l'émission d'un photon. If the energy of this metal is less than the energy of the radiation, when it is subjected to that radiation, there is going to be a production, or bien there is going to be a transition, yes, of this electron from energy state number 1 to energy state number 2. Then it is going to be accompanied by the emission of a photon. Now, why is there emission of a photon? It is because there is a energy loss. So in other words, what I'm trying to say is, I'll use this principle on chemical energetics. So we are saying for every reaction that loses energy, enthalpy change is equals to negative delta. So that means their enthalpy is negative, and it implies that the reaction is exothermic. There is heat loss. This is what we're trying to explain here. Because there is heat loss, heat is expelled to the environment, then the energy reduces. When there is energy absorption, which is enthalpy, energy change is equals to positive delta, it means that there is an increase in the amount of energy from the surrounding to the system. Is there any question so far? Then maybe another highlight. The energy formula you're seeing here is basically Albert Einstein's, no, sorry, not Albert Einstein. Yeah, okay, it's Albert Einstein and Planck. So this here, E is equals to H for V. H simply stands for Planck's constant, which is equals to 6.6 times 10 to the power negative 32 joules per second. And this V here stands for velocity, not the speed of light, but velocity. So it can either be the velocity of light, it can be the velocity of any particle. But what this equation here simply explains is what we call de Broglie's principle of matière-rayonnement. De Broglie explains to say that particles in one state exist as waves, and waves exist as particles. For you guys doing medicine, unfortunately, we're not going to go in that info. Are there any questions so far on the energy interaction, matière-rayonnement? So we have energy absorption and energy d'émission. Any questions so far? Okay, we continue. Then this was his second postulate that has two parts, the absorption and the emission. Now we have the last one that explains the principle of angular momentum. Now you ask me, what is angular momentum? So angular momentum is a property characterizing the rotation of an object in a motion. It's just like angular momentum is the momentum that keeps an object in circular motion. Now we're going to explain that when we look at the electron. So this is a diagram just showing that this is energy d'émission. So when it is moving from a lower energy, from a higher energy to a lower energy, there is a ejection of a photon. Then I'll start from this side now. From a higher energy to a lower energy, that's emission. So there is energy that is ejected. From a lower energy to a higher energy, energy is absorbed to the system. Then this one here, this is an electron in its dormant state, in its what's this, neutral state, where there is no interaction between the electron and its energy levels. So this is a brief description of Bohr's atom. So Bohr's atom describes the circular orbitals that they are bien définis autour d'un noyau. So like I said, his first postulate explains the principle, or bien explains how orbitals are oriented in an atom. So he says that the electrons are décrits d'orbites circulaires de rayons bien définis autour d'un noyau. You find that all electrons are found in definite energy levels. Yeah. So then we have the second principle that explains the energy absorption and energy emission, which is the second postulate. Then the last postulate, which is the one that explains the principle of angular momentum, states that an electron will always be found in a circular motion. Why? Because there is always going to be a nuclear charge that is going to help with its position. You know, the reason why electrons are found in these energy levels is because of the nuclear charge that exists between the noyau and the electron. This is now where you come to talk about principles of energy deionization. You talk about reactivity of different elements. When you talk about the repulsion forces between the nucleus and the furthest electron, all those things. Then the energy levels, like I said in is it organic chemistry, when we're looking at hybridization, we said the energy levels of an atom define the period in which that atom is found in. So take for instance, if this is the atom we are studying, then these are the number of energy shells or orbitals that we have. It means this atom is found in period number 1, 2, 3, 4. It's found in period number 4 of the periodic table. I can assume to say that this will be a calcium atom, because the calcium has got, I think, calcium is found in period 4. Yeah, calcium is found in period 4, same as potassium. They are all found in period 4. So are there any questions so far on Bohr's model? Okay, so Bohr's model further on describes the Royan. Okay, these formulas are not needed for you guys, but I'll just explain them. So Bohr's model explains the variation of the radius over a given energy level. So this A here you are seeing is a constant. This A here you are seeing is a constant. It signifies how many nanometers that Bohr had calculated with reference to the hydrogen atom. He found out that the Royan for a hydrogen atom is equals to 0.9, sorry, yeah, 0.52 Armstrongs. So that was the radius that Bohr found for the hydrogen atom, because it only has one N. It only has one energy level. So that was the radius. Because you guys are doing medicine, won't bother you with the derivation of where this radius came from. So we are saying that the constant of the radius for the hydrogen atom is equals to 0.29 Armstrongs. Then the energy, whenever you're calculating energy for a given energy level, we take the energy formula to be equals to energy for any given state N is equals to negative 13.6 divided by N to the power 2. It is equals to negative 13.6 over N to the power 2. So the N here signifies the energy levels. The N signifies energy levels. So you'll be taught to calculate the energy of an electron when it was absorbed or when it was emitted. So you apply the same principle. Energy d'absorption is the energy that you are going to emit. The energy, the emission is the energy we are going to emit. And this is a transition from a higher energy state to a lower energy state. Then energy d'absorption is the energy we are going to absorb, which is a transition from a lower energy state to a higher energy state. So I'll show you guys examples on how to calculate energy related questions. So, a rappel, 1 electron volt is equivalent to the electron charge, now in joules. So an electron volt is also an energy quantity or an energy measure. An electron volt is the same as an electron measure. So one electron volt is equivalent to 1.6 times 10 to the power negative 19 joules. If you guys can remember very well, the charge of an electron and the charge of a proton is equals to 1.6 to the power negative 19. That is positive 1.6 times 10 to the power negative 19 for the proton, and negative 1.6 times 10 to the power negative 19 coulombs for the electron. Then another parenthesis, nombre quantique principal, N, signifies the principal quantum number. For now, principal quantum number will be explained further, but it explains or defines the principal quantum number. So the principal quantum number is just the state or the number given to a particular energy level. The quantum number is the name given to a specific energy level. So this is Modèle de Bohr. Then we have how the energy formula came about. Now this part just explains the forces that act here, and it just defines, it's just a summary of the three postulates. The first one explains the principle of energy being standardized, or bien having stationary energy levels where you find electrons. Then the second one explains the principle of energy d'absorption, energy d'émission. Then the last one explains the principle of angular momentum. Now, angular momentum, this is where you apply, this is what you call angular momentum. So for you guys, unfortunately, this is not necessary. So, but this is angular momentum, also known as la moment cinétique orbital et quantifié. Then for the Roignon that I was talking about, for those that want to explore, if you want to find out the Roignon for this atom here we have, you just replace these constants. So you can be writing down that as if you want. So you're saying n squared, which is 1, z, which is 1, h stands for Planck's constant, which is 6.6 times 10 to the power negative 32 joules per second. E, which is epsilon, is equals to 8.85 times 10 to the power negative 12. Pi is equals to 22 over 7. The mass of an electron is equals to 9.0 times 10 to the power negative 31 kgs, because note, we are putting all these units in standard units, kgs, joules per second. Then the electron here, electron charge. No, this is mass, sorry, this is mass. This is mass of an electron.
I'm sorry, Daliso.
Yeah.
I'm very lost.
No, as in, you're lost on this part. Or everything. Or this part.
The beginning of this slide.
This slide.
Yes.
I think I just skip it. Okay.
This slide.
This one.
This slide with the
this
formulas. Both.
This one.
Both.
No, for this one, please. Like I said, I'm just explaining this to just at least you guys should see these things, but it's not necessary for you guys. But I'll still re-explain. Bambi, guys, anyway, such I explain. So we are saying Bohr's model explains the three postulates, or bien four. The first one states that an electron is found in a specified energy level. This is a specified energy level. The hydrogen, note, please take note. Bohr's model is an explanation of the hydrogen atom. Why? Because the hydrogen atom is the simplest atom that you have on the periodic table, and whatever you study on the hydrogen atom will be applied on every other atom. So Bohr used the hydrogen atom as reference. Then later scientists were building from what Bohr was explaining. Now you find out that Bohr's principles were disqualified when you look at other people that studied the atom. Was disqualified only because he used the hydrogen atom. He did not justify with other atoms. You see, he used hydrogen. Now people were asking him, okay, it works for hydrogen, but what about if we to use potassium? What's going to be the case there? What is going to be the case? So now this is where the debate and the four of his principles came about. But now we're just studying the hydrogen atom, and we're saying the first principle states that the energy levels of a hydrogen atom, of an atom, they are specified or they are specific, and you'll find electrons in this stationary energy levels. Then these formulas, please, these formulas, don't look at these formulas. Just hear what I'm telling you. These formulas, they'll confuse you, and you have fear, and these formulas aren't for you guys. But what I was just trying to say is, the second principle that explains energy absorption and energy emission states, because there is a nucleus here, the nucleus here has got a charge. And this nucleus also has an effect on the electron. Or in other words, it is because of the nucleus that we have the electron moving in this orbit, because the two are opposite charges. You guys that are doing, the engineers that are doing electrostatic, understand these principles very well, because here you even have the derivation of Coulomb's law and all those things. But for you guys, that is not important. So what I'm trying to say is, because there is a nuclear charge between the atom and the nucleus and the electron, there is going to be energy variations. The energy variations that we have here are in two. There is the first one, which is energy d'absorption. Energy d'absorption is the movement of an electron from a higher energy level to, from a lower energy level, energy level to a higher energy level. Have I lied? Absorption is the movement from a lower energy level to a higher energy level. I'm pretty sure some of you are confused. Absorption, the movement of an electron from a lower energy level to a higher energy level, energy d'absorption. Energy d'emission is the opposite. It is the movement of an electron from a higher energy level to a lower energy level. So now, this diagram here just shows you the types of forces that you have here. Like there's a centripetal force, which is this one. There is a force that the charge and the electron have in common. No, I'm saying all those things are not necessary, but you just have to know that, okay, this is what happens. I'm pretty sure you guys know what happens. The nucleus and the electron remain in balance because of the force that exists between the two. This one is positive and this one is negative. You know what happens to two charges. You guys have done electrostatics for Z. When two charges, two opposite charges are in contact, what happens? There's attraction. So there's an attraction force here between this noyau and this electron. SAF. If I'm a formula, if no, they're not yours. These things are not yours. It's just that this polycopy is just too advanced. Now we come back to this part here where I was explaining the principle of angular momentum. So we're saying angular momentum is the momentum or a characteristic of motion that keeps a particle in its orbit. As this thing is moving, as this electron is moving in this direction, because there is centripetal force. You guys know what centripetal force is. The force that keeps a particle in motion, in a circular motion. Centripetal force. So because this particle is in motion, there is also what you call angular momentum. There is a velocity here, and we are saying this particle here has a mass. Momentum is mass multiplied by velocity. So even as this electron is going to be moving in this orbital, there's a velocity that it's going to have. Now, because we know that the electron also has a definite mass, which is 9 times 10 to the power negative 31 kgs. It means it's also going to have a momentum, even though it's having another factor here called centripetal force. It's also going to have angular momentum. So the motion, or bien the momentum that keeps an object in circular motion is called angular momentum. Then the force that keeps a particle in motion is called centripetal force. There's also what called centripetal acceleration, but we're not going to go in those ends. So for you guys that are interested, those that want to just prove these formulas. So to prove that the momentum ou bien the moment cinétique orbital est quantifié, you can, this is where I come in, Esther. This is where I come in and say, no, if you want, these things shouldn't bother you. If you want, I'll just give you the constants. Then, you replace them. So we are saying the mass of an electron multiplied by the velocity multiplied by the radius. So the mass of an electron, we know that that's 9.1 times 10 to the power negative 31 kgs. The velocity, we are going to find the velocity, but the velocity is not really important because when you start calculating velocities now, it will bring for now, the velocity is not important. The radius as well, it's given in certain what's this, units, either in nanometers, in picometers, in Armstrongs, etc. Then N stands for the principal quantum number, which is actually the number that defines these energy levels. H is Planck's constant. You know what pi is? 22/7. Same applies to this one. For those that are interested in this conservation, if you want to convert this, like I said, the formula is just simple. The formula is A multiplied n to the power 2. But for those that want to just verify what it is, it can also be written as Rn is equals to 0.529 Armstrongs for n carré. Yeah, it can also be written like that, or it can be written in this form. It can also be written in this form. So, like I said, please, these formulas are just there to just explain what's happening, but you are not supposed to take them at heart. Yeah. So this is how the energy formula comes about. This energy formula you're seeing here, was derived under, we had all this. So now we go to, these are just some of the conversions, Kelvin unit. So the mass of an electron is 9.1 times 10 to the power negative 31 kgs. The speed of light 3 times 10 to the power 8. Electron charge is 1.6 to the power negative 19. E, which is epsilon, is equals to 1/4 pi times 9 to the power 9, which is equals to 8.85 to the power negative 12. Planck's constant, Planck's constant is 6.6 to the power negative 34. Then we have electron volt, Armstrong, nanometer, micrometer. So these are some of the units that you are going to find in this lecture. So now, hydrogen atom was subjected to different radiations, like we were saying. We're saying, no, this atom, after energy d'émission, energy d'absorption, all those things. At the end of the day, when there was experiment, there's what you call the double slit experiment. I think you guys have heard it before. There's what you call the double slit experiment. So after the double slit experiment was done, it was found that the hydrogen atom has spectra, what you call a spectra, like a spectrum of different colors. Now those spectrums, or the spectra that the hydrogen atom produces actually shows energy states. It shows energy states. So there's what you call infrared radiation, visible light radiation, ultraviolet radiation. So all in all, when the hydrogen atom was subjected to radiation, you can also look up this, it's called the double slit experiment. When the hydrogen atom was subjected to a radiation, it produced different radiations of different wavelengths. In other words, what I'm trying to say is, you guys know what the electromagnetic spectrum is. Is the electromagnetic spectrum. You've done this in physics. So, yeah, there's what you call the electromagnetic spectrum. The electromagnetic spectrum varies in two things, two important things. One is the frequency, and the other one is wavelength. It's the same thing that's happening here. So when the hydrogen atom was subjected to radiation, it produced this type of arrangement. We have things like infrared radiation. Take for instance, infrared radiation has got a wavelength of 2. Then visible light has a wavelength of 6. Ultraviolet radiation has a what do you call this? Wavelength of 10. So it just shows the variation of these electromagnetic waves. Now, when we translate this in the form of the energy diagram, this is an energy diagram, the one that shows the stationary energy level. So like I was saying, his first principle explains the idea that energy levels are stationary. This is what we mean by they are stationary. So you find that for infrared radiation, it's found in between energy level number 7 and energy level number 3. This is where you find the energy infrared radiation. Then at at 7 to 2, you find visible light radiation. At 7 to 1, you find ultraviolet radiation. Yeah. So basically, what happened was when the hydrogen atom was subjected to further experiments, it was found out that it actually emits or produces what we call a spectrum. Now, we know that spectrum is made up of different radiations that differ in their wavelengths and their frequency. The difference between infrared and visible light is basically their frequencies and their wavelengths. So, are there any questions so far? Guys, let me not bore you. I think this is the end of the lecture. Are there any questions? Yeah, this is the end. Yeah, Inaka. Are there any questions? Huh? Are there any questions?
There are no questions.
Is it that you are tired, or Shan?
We are there, Delisa.
And I'm also tired, you guys. I'm also tired. But are there questions? Because the next time I'm coming, Modèle quantique de l'atome. Une question. Tout va bien.
Questions, boss. Questions.
You have a question?
Oui. C'est une question.
Okay. Alhamdulillah. Guys, on se verra, inshallah, in an inaka. So, this is the end of